Okay, so in this video, I just wanted to briefly go over line integrals, their definitions, maybe a couple of examples. This hopefully won't take too long. It might end up being 2 videos, we'll see. But okay, first, kind of the stuff we already know that we did earlier in the semester. In order to define this line integral, we're going to have some smooth parametrized curve C. We know what smooth means. It means it's twice differentiable. And while not listed here, a lot of the curves we actually work with will also be simple, which means that all reparametrizations are one-to-one. All the stuff we've already mentioned earlier, but we have this parametrization R of t, our standard x of t, y of t, z of t. We want a function of 3 variables with a domain that we'll just call d of f for the domain of this, and per everything we've done before, the curve C will lie in the domain of f. Now, in order to get our line integral, we have to create what your book calls the pullback of a function. I don't necessarily like that terminology for it, but it doesn't really matter. It's just a composition of the function f composed with r of t, which is, again, the exact same thing we did earlier in the semester when we were working with parametrized curves and functions and finding their compositions. Now your book just calls it a pullback, but it's still the standard composition of functions, f of r of t, which is f of x of t, y of t, z of t. So just on the off chance we've maybe somewhat forgotten how that works, I don't think so, but suppose we have r of t is equal to this, f of x, y, z is equal to that. Find f composed with r of t. But that's just f of r of t, which is f of sine t, t. Now I plug in and I'll get sine squared of t times y, which is et, plus y, which is et, times z, which is t, plus z, which is t. And there I get my composition or my pullback or whatever you actually want to call it. It doesn't really matter. Again, we've done this before, but we actually want to use what we did before in terms of parametrized curves and functions and their compositions. And in the past, when defining integrals, we have found Riemann sums and done all of that. And you actually can do that here, but now we're going to do this more in an algebraic way, using what we did for integration earlier here, and just kind of manipulate it. So, here's the idea, and I will point out, again, this is somewhat brief compared to what we did in class. Your book does give a much broader version of it. I'm just not necessarily doing that here because I already did it in class one time. Okay, so when we worked with parametrized curves and functions, we generally talked about, well, the helix was our standard example, and we then found the arc length parametrization. And we said that there were a lot of different parametrizations, but the arc length was kind of the standard one that we worked with. So we're going to use that here. And when we defined it, we said s of t was equal to the integral from a to t of the magnitude of dr d theta, sorry, dr d sigma, bad Greek, dr d sigma as t is between a and b. And we had that right here. And now, like I said, we're going to work on this more algebraically. I'm going to take s prime of t. And you're all aware of the fundamental theorem of calculus, so you know how this works. S prime of t will just give me, well, we'll do it this way first. There's multiple ways to do this. I want to follow more or less what I did in class. If I take the derivative of this, then I just get the magnitude of dr ds. And put my little symbol right there. I'm sorry, t, wrong variable. Too many variables. We get that right there, which is, again, nothing new, even though it looks different. It's the fundamental theorem of calculus. But the other way to define s prime of t is just ds dt. And now, when you work with the fundamental theorem of calculus, going all the way back to Calc 1, a lot of times you find differentials. If I want to find the differential ds, I actually have 2 different ways to write it now. I can multiply the dt here or here, which means s prime of t dt is equal to the magnitude of dr dt times dt or ds. And again, this may seem a little bit odd, but I'm more doing an algebraic trick to develop my integral as opposed to doing the Riemann sum version. But now, well, this right here, I suppose, if I don't necessarily want to write the magnitude, dr dt is just r prime. So maybe we'll rewrite this. S prime of t dt is equal to r prime dt, which is again also equal to the differential ds. So we have that right there. But now, when we did our integrals before, we had the integral along c of f of x, y, z ds. But now I'm going to use what I did here and just algebraically manipulate that. In this case, I'm going to use my composition, my pullback. So this will be the integral from a to b of f of r of t. But then ds, using this right here, my ds I can write in either of these forms here. But ultimately, since this is in terms of r of t, I want to have my whole integral in terms of r of t. So I'll use this form right here. R prime of t dt. And now I have this nice integral that I can solve completely in terms of t, and we call this the line integral along a curve. You can also call it a path integral. It has lots of different names. When I was in school, my instructor called it a path integral, a line integral. It doesn't really matter. But well, now I have the formula for an integral that's called the line integral that I can solve. And again, we didn't generate this integral from a Riemann sum perspective, but we used an integral that we already knew from earlier in the semester. And then I more algebraically manipulated it to get another form of the integral. As far as using it, let's see, I have several examples in here. Okay, we'll do this one. As I have said in class multiple times, going all the way back even to Calc 1, the hard part is maybe deriving the formula for the integral. I mean, you have to do the Riemann sum thing, or in this case, some algebraic tricks. But once you do that, yep, the video's still working. Okay, once you do that, once you have a formula for the integration part is actually easy. I mean, let's face it, it's either going to use the rules of integration that you already know, or if it doesn't, then you can't integrate it by hand, you're going to throw it into Maple and have Maple integrate it. So the hard part is kind of deriving the formula for it, and in this case, we just did some algebraic tricks to derive this one. But now, suppose we have this. F of x, y, z equals xy plus yz plus zx. And r of t is equal to 2 cosine t, 2 sine t, t, which is, of course, the helix that I'm used to, that we did before. I want to find the line integral along that curve. Well, let's see. In order to do that, I'm going to need f of r of t and the magnitude of r prime of t. So f of r of t first, I guess. I can do it right over here. F of r of t is f of 2 cosine t, 2 sine t, t, which is, let's see, x times y, so that'll be 4 cosine t sine t, plus yz, which will be this times this, so So that's 2t sine t plus zx, which is 2t cosine t. A little bit cumbersome, but not that big of a deal. So that's this. Now I need the magnitude of r prime of t. So first I find r prime. The derivative there would be negative 2 sine t, 2 cosine t, 1. And now I'm not going to do all the calculations out for this. It's not that big of a deal. To find the magnitude of that, we've done it in class repeatedly. Square this, factor it, Pythagorean identity. This will end up being 4 plus 1, and your magnitude will be root 5. But now, I have all the information I need on my small little board. Now I just need to set up my integral. So the integral will be from t goes from 0 to 2 pi of f of r of t, which is that, for cosine t sine t plus 2t sine t plus 2t cosine t times the magnitude, root 5, and here, since that's a constant, I'll just pull the root 5 all the way to the front of the integral, dt. And then just solve that. And I'm actually not even going to take the time to do all the calculations out. All of you can integrate that. U substitution, integration by parts, solve it all out. There's different ways to go. Get the integral, and the actual value should be negative 4 root 5 pi. And I would point out, this is a new thing, this idea of a line integral, but, well, it's based off of a formula that we already had, so there's nothing really new there. We've already done this repeatedly. Like I said, we use the helix here because we've actually done all these things before. Calculated this, calculated that. The integral is just a single integral, not a double integral, not a triple integral, nothing confusing like that. And, well, the integration part is, again, incredibly straightforward, because if it wasn't, you couldn't actually solve it. Good, still under 15 minutes. The real reason we use this is because ultimately we want to do this for a general vector field as opposed to just one curve like this, and look at surfaces and things like that. But in order to do that, we need to kind of start here with stuff we already know and then build up to what we want. A couple of things to point out, and I'm going to have to make another video and I'll go through one more example of this that's a little bit more involved maybe, just so we're clear. But we did our arc length parametrization earlier in the semester, and we always used r of s, which is actually what our original integral was. It's in terms of ds. And yet here, this integral I do is in terms of t. The s disappears, which is what happened before, essentially because as far as it goes, all of these integrals are independent of your parametrization. Meaning, again, if we recall what we did earlier in the semester, I don't necessarily have to go through all the work of finding a specific arc length parametrization for a function and do all of that. Any parametrization will work, so this is completely fine right here in terms of t. I don't need to convert to s and do all of that. Okay, this is just about at 15 minutes, which is the limit for uploading my videos to YouTube. So, like I said, I'm going to end this, but I'll make another video doing one more example of this.